In this video, we are going to work on anomaly detection with accounting data and specifically with external financial data. And this external financial data, what we usually care about when we're looking at that is whether a company is manipulating their reporting. If we had internal financial data, we might have different details and more specifics about individual transactions rather than something aggregated at the company level. So the same techniques could be used, but the type of data would be different. One of the challenges when we are looking at data where we are trying to identify anomalies without having a set of coded variables where we know there were problems is that we just have to look for things that are unusual rather than predicting whether they are fraudulent or managing their earnings. In the earnings related week where we talked about predicting bankruptcy and predicting restatements, we already addressed where we're trying to model observations where we know that there were problems. Here we're trying to deal with ones where we don't know if there are problems and then finding techniques to be able to find which observations are unusual. So we'll take the framework from this external financial perspective. I'll show you some of the concepts that have been used in this area, and then we'll apply a few different methods for coming up with anomalies in the data. We're going to use some of these packages that we've used before. So we've used all of these up to here. We're going to introduce 3 new packages. FNN is fast nearest neighbors. It just helps to speed up identifying nearest neighbors, and specifically we're going to find observations that are not very close to other neighbors. There we have this bidimensional regression. We haven't done that before. It's basically a regression, but it's doing 2-dimensional prediction and trying to fit a 2D plot and how use some predictors to do that. And then the last one is isolation trees, and that instead of trying to predict specific observations, which we've done in the past with regression trees, it's trying to predict which ones are unusual, which ones are furthest from observations nearby. So if you want to learn more about these, I've added some links that you could go look at, some websites that talk about these. We won't go into lots of detail on the specifics of them. I will try and explain some of the intuition behind them as we get to them. We're going to use some of these functions we've already used before. Here are the new data sets. The financial data or the accounting data one is going to be very similar to what we've seen before. This earnings management one is going to be similar to the restatement data we had before, but this one is specifically looking at earnings management, meaning financial statements were caught as being important enough that they're affecting the reporting of the company and look like they upwardly manipulated financial information. So we're going to combine this, the same thing. We're going to, we did this before. We're going to take the restatement date at the beginning and the restatement date at the end, and we're going to put the financial data in between those 2 dates, and we're going to merge by GV key. And then if we have, when we merge that in, there are going to be missing values for where we don't have earnings management identified. So then we need to set that equal to 0. If you look at the data and how many in there have earnings management, it's quite small, smaller than we had before with all restatements. So, a really small fraction of the data has earnings management. So this is one reason we need to do unsupervised anomaly detection, and it's just to learn this sort of process too. So I'm going to remove these because I don't want them hanging around. Then I'm going to introduce a new transformation to the data just because I think it's fun. So if we have unscaled data and we have really big outliers sort of on both sides, then a simple removing the outliers still doesn't make the data look too great. And it can be very skewed, at least in this accounting data. So we're going to do what is called a negative log transformation. And all that is if you have negative and positive values that are skewed or that have really long tails, it's going to take the natural log of the positives and then separately the natural log of the negatives, but it's because we can't take a natural log of a negative number, then it's going to use the absolute value of that and then put the sign to be positive or negative again after you've done these log transformations. So if you want to read up about negative log transformations, you can go do that, but this is one way to do that. Then there are lots of choices about what we could use to try and predict earnings management. So I'm going to talk about just a couple that are used all the time in the accounting literature, but then others I'm just coming up with stuff, so I don't know. So net income, this is the thing that we're interested in, whether it's been manipulated or not. So of course this goes in there. Accruals is the difference between net income and operating cash flows. So a quick review of what accounting information is, that we have net income, and that is the accountant's version of earnings. And it has some things in there that are not operating cash flows. So a company could collect cash and spend cash, and that may not match up to the income item that the accountants record. And that's because there are judgments that need to take place when you're calculating net income, things like depreciation or accounts receivable or other things like that are non-cash based. And so most of the earnings management literature has begun with the non-cash portion of net income. So they take out the cash flows and only look at the difference between cash flows and net income. And then we'll have cash flows. These other ones are just variables that I thought they might affect what's unusual or what's usual. And so I'm not really too worried about any of these particular variables, but we'll mess around with them a little bit. If we really wanted to do a great job, there's a chance we could go after and try and put in a lot more variables and really understand what's going on as well. But these are sort of standard ones in the literature. And then I'm taking all of these ones that we just created here, and I'm going to transform them here so that they will be natural log. It'll pull in the tails of the data set or of each of the variables. Then we've used standardized before because we're going to do some distance measures. So we've talked about that when we did the some of the earlier methods that require distances to calculating from various variables. Well, sometimes we want to standardize them, so we're going to do that here, and we'll try a few different methods and see whether standardizing matters or not. All right, so all of this is to create all of the variables that I want to use. I'm going to remove missing values because we have some lag rows in there that we won't have data. And then I just want to simplify. So I'm removing missing and only keeping the variables we're going to work with. And once we do that, take just a second, we're going to look at what the transformation did to the data. So we'll first plot this net income without the transformation. And you can see, you can't even see the distribution, and that's because there's some really large negative values and really large positive values as well. And I realize I'm not showing my whole screen, so I'm going to change that in just a second. Now when we do this for the transformed version, notice we can see the whole distribution. There's a chance we kind of, when you do scaled and take out the outliers, there's more of a peak in the middle here. So perhaps this transformation is moved a little bit out from this middle to each side a little bit. And we could mess around with that as well, but that's, at least it's a usable distribution. Then we've done this before. We're going to set the seed, and I'm going to keep 60% of the data to use as the training data set. All right, so let's start talking through some different ways to look at unusual or anomalies in the data. So the first one we might do, remember we're talking about net income, and we think that companies might push their net income higher than it should be. Well, we could just look at this net income distribution and say, well, higher ones are more likely to be manipulated than lower ones, which could be the case. But then there are also ones in here that are real earnings and have not been manipulated. So it messes things up a little. But that's sort of the first one. So in that, we would be looking at really high net income. Is that more likely to be manipulated? Not the best measure, but or conceptually not the best measure, but it's where we usually start. The next one would be, as we talked about, if we have this accruals, meaning the earnings part are higher than the cash flow part. So the part that accountants are adding to the earnings number, if it goes up, maybe they're manipulating a little bit more. But again, we're going to have something that looks very similar to the net income distribution, so we don't really know, it's still there. And what I'm going to do here is I'm going to name each one of these measures we're using as unusual income. I'm going to put over here and save it in the training data set. So this first one I'm calling unusual 1, the second one unusual 2, and then we'll keep going through down. We'll have 9 of them, I think. Okay, the next one is very common in the literature as well. Is what we're going to do is we're going to say, let's take the earnings, the non-cash earnings part, and let's model what's normal for that level of non-cash earnings. And so PP&E, the reason they put that in there is because property, plant, and equipment has to be depreciated, so that goes into accruals. They put in change in sales. I don't know why they do that. Because growth, you have higher accruals is the concept behind it. And then they do some sort of way to control for size. So sometimes they divide by assets, or you could do something like this to put it in there to control for it. But we're just running a regression. And then what comes out of that is what we want is the part that wasn't explained by this model, because the part that is explained, we're going to say are normal levels of non-cash earnings or accruals. So we've done these sorts of things from the Broom function before. Here we're going to use augment, and what augment does is take the original variables, these ones that are already in here, and add in some other variables from the regression. So let me show you how that works. So we're going to run it by year, then group by year, and then run this regression by year. And we go over to the out data frame. So notice we have all of the data that we've used for the regression, but then we have the fitted value. That's what the model predicts that would be. The residual is the difference between what was predicted and what actually was there. So this 0.52 minus this negative 0.66, this is the residual. So it's higher than would be expected based on this model. And then we have some other things in here we could use as well from the regression. Okay. So then we're just going to save that residual, meaning the part that is unexplained by normal. We're going to just put that in there as part of the model. Of course, we're doing negative to positive. That meaning we are going to identify those that are higher abnormal as earnings management. We might think about higher or lower, and that might give us a different sort of measure than this. So we might use like absolute residuals or something, if that's what we were interested in. Okay, so we could do the same thing we have here, but instead of doing accruals, we could just directly do net income, because the thing we're interested in is unusual net income. So all I did was change net income, put the part we think is normal is cash flows over here, and then all the other things the same. I don't know. Oh, I didn't put in change in revenue because I thought maybe we should do a predictive version where none of these other variables we don't know about were at the same time as the net income. It's kind of arbitrary. I just was messing around with it. So we do the same thing, save another unusual. I'm going to call this number 4. So those are all the sort of standard ways that have been thought of to identify anomalies in earnings management sort of literature. So let me introduce something else. So we're going to do a couple of other ones, and this one is the nearest neighbors. And we talked about doing these nearest neighbors, and we can see how similar a company is to another company. Well, we can sort of reverse the idea and say, let's take one that is very different from another company, and we're going to use this fast nearest neighbors function, package. And here, because we're going to measure distances, how different companies are, I'm just going to use all of the standardized variables that we've used. Of course, we might or might not want all of these variables in there. I just threw out all of the ones in that I know, or that we already created in the data set, but we might want more or less. Well, first let me get this data frame for us. So we're going to do this data frame. Then this first part is the function for the fnn package. And what it does is take that data frame you just created, so it's going to use all of the variables that are in there, and then says calculate the k nearest neighbors, and here we're going to calculate 50 nearest neighbors. So we go ahead and run that, and 50 is just like a guess. We don't know. It's like a tuning parameter where we can mess around and try and find the number of nearest neighbors that we should use, and it's a little bit arbitrary. You'll do something of that in the homework, but we don't really know. So it runs, and then what's going to come out of that once it's done is this nn.dist. So in that object we just created, it has an object nn.distance. So what this object does is show you the nearest neighbors for each observation. Here I'm just going to look at the top 5 rows and the top 5 columns because we don't want to look at a huge matrix. So then in the first column, so the first row is the first observation in the data set. The first column is the nearest neighbor, the neighbor that is the closest to that first column, the first row's data. The next is the next closest, so you notice as you go from left to right, the ones in column 5 are more different from the ones in column 1, and we can see some differences across rows as well. So this first one has some observations that are sort of similar to that row, to that observation, whereas row 5 is different from these more than others. So in row 5, at least for the first one, we would say it's more different from other neighbors than is, let's say, number 1. So we can use that as just how unusual is the company. We could use the first one, right? Just use one single nearest neighbor, or we could average across a lot of them. One of the reasons why we don't want to just use the first one is because some of these companies are in there multiple years in a row, and if they could look just a lot like their other observation in the data, so that may not help us identify something that's unusual. It just identifies that it's in there again another year. So we're going to save this as the unusual. I'm going to call this score unusual for right now, and I'm just going to do the mean for each row. So here it's the row means function, and it's just going to average across all of these columns in each row, and it's going to do that it's going to have 50 columns, and it's going to average across all of those. So if we want to look, we could look at what that unusual score looks like, and notice it has a lot that are fairly close, the 0.13, 0.14, but we have some up here that are large, so near 1 or over 1. So we would call those larger ones more different from the neighboring observations. So we're going to save that as unusual. Notice the difference here is unusual here means the observation is unusual. Up here we're talking about accruals or net income itself is unusual. So we're twisting things just a little bit, but the concept is sort of still the same. We're trying to identify unusual observations, these anomalies in the data. Of course, let's go back to this net income graph here, this histogram. When you look at a single distribution, a single graph, it's not always so easy to identify something that is an anomaly because this data is pretty good, and it isn't very mechanical. So something that would be an easy anomaly to detect, we don't really have that in this sort of data. Some other anomalies that are there because in a transaction someone transposed a number or something, those are easier to detect in mechanical sort of systems, but this isn't one of those. All right, so then we'll do another one where we're just not going to standardize the variables. So remember we talked about when we're creating a distance measure, sometimes standardizing is important. We'll just do it here where we don't standardize them, create another score, and we'll just see how that performs when we go to test it. Okay, we're down to our last two versions of anomaly detection. We'll do two of this version and then one of the next one. So this we're going to call unusual 7 and unusual 8. This is called a bi-dimensional regression, and really what that's doing, and you can go look at this paper that did it, it's pretty interesting. But I actually have a hard time, it takes me a while to think about what it means when you're doing a bivariate regression. So what we really care about is, are there places on the graph where a variable doesn't, an observation, a two-dimensional observation doesn't seem to belong at that point in the graph. And to show you how, why we're interested in that, let's do this. We're going to graph cash flows and net income together. So remember, the net income and cash flows are what accounting people really care about. So if net income is different from cash flows, then we throw it up as a red flag. Well, when we graph this transformed data, it looks a little bit different than if you don't transform it. So, maybe this is great, maybe it's a good innovation, maybe it's not. And by the way, there are lots of dots, so it takes a while for it to show up. But something interesting comes up when you do transform them. Notice it looks like we've got a line going down this way, a line going up this way. So it's sort of like we have a normal group that is positive and a normal group that is negative. Well, if we run a linear regression, we're not going to pick that up at all. And so we're missing that in some of the other anomaly detection versions. And so if we're looking here and we can identify that this right here is, maybe that's an anomaly relative to this one, right? But this is, if we compare it down to this one, well, then or let me give you a different one, sorry. We compare it to this one, of course, it would still be an anomaly. If we look at this one here and we say, well, that's not really an anomaly, it's sort of close to the line that you're supposed to be on. But if we compared that dot to down here, then or to over here, we would say it's an anomaly. So the hope is we can better classify anomalies because we're comparing them around here. So notice this is going to be pretty similar to the idea of just looking at nearest neighbors, because you're going to compare across these groups here. The difference here is nearest neighbors is going to use all of the variables. Here we're just going to do two-dimensional. And when we use the regressions, we're not doing, we're trying to do a line that's not going to fit something that's nonlinear. Okay, so let me just talk a minute about how we set this up. So this package is from this package here, and it requires a couple of specific ways to set up the data to be able to use it. And we can only use, because it's a bi-dimensional regression, we can only use 2 dimensions in the y variables and 2 dimensions in the x variables. So we're limited and we have to make some choices about which variables we're going to use. So because accounting people are really interested in this net income and cash flows, we're going to compare those two, right? And that's this graph over here. And I'm just going to choose the prior year's assets, the prior year's revenues. I don't know if those are the right ones to do. So we're going to go ahead and use those, and they have to be called dependent variable 1 is the first one. So I'm going to use scaled net income here. Standardized net income here. And I'm going to use standardized cash flows here for the second dependent variable. So this is like the x variable and the y variable that you're trying to fit on those 2 dimensions. The independent variable 1 and independent variable 2 are the other 2 that you're going to try and use to predict these other, the dependent variable ones. So we need to keep those in there. I'm going to also keep GV key, F year, and the ones that are the real ones, right? So we're going to try and predict SNI and SCF. I'm going to also keep actual SNI and SCF in here so we don't, so we can use it later. All right, so I run this to create a new data set. So if we look over at temp, you'll see we have the dependent variables, independent variables, then other stuff that we're trying to collect. I set this up so that this one is the dependent variable 1, this one is dependent variable 2, but these won't be affected by the method, the function we're using. So then once we go ahead and run that, this is LM2, so two-dimensional linear model is what I think it's supposed to stand for. So we have two y variables, the modeling tilde, and then the two x variables, the data set that we're going to use, and then the method. And there are three different methods. Euclidean distance, that's what most of the k nearest neighbors and clustering methods use. The affine and the projective methods, these basically are just more complex than the Euclidean method. So we'll try a different one too, but we'll start here. So we run this. Let's look at what the summary looks like once it runs. And some of it, if you want to spend some time with the paper, you can sort of try and interpret some of this. But the main part that I think that is worth focusing on is this r squared here. These two x independent variables, not x, I gotta be careful. So independent variable 1 and independent variable 2 help explain the location on the two-dimensional graph here. About 35% of that variation they can explain here. So it's not perfect, but they sort of get it. So then let's try the other approach, the affine model or distance measure. And here it gets 37%. So it explains a little bit more of how this, of where these points on the plots are. So we'll try both. Okay, so then how do I use this to predict with? Well, from these we have to, when we do the predict function, we need our model, which is what we created up here. And then we can only have the two variables that we are using for the prediction. So 3 and 4 here. If we go back to the temp data set, 3 and 4, so this is column 1, 2, 3, 4. So column 3 and 4 are the ones that we are using for the prediction. So I'm going to use that here. So we're going to predict with the model we have and the independent variables that we used. And what will come out of that is a prediction. So here, oops, I forgot a ending parentheses. And you'll see we have now a prediction for what the the dependent variable 1 should be and dependent variable 2 should be. I don't know why they did x1 and 2. So then we can compare those to the actual dependent variable 1 and dependent variable 2. And how we're going to do that is combine the actual ones, the outputs, the predicted, with the actual. So remember we selected these two. So we're going to combine these together into a data frame, and we're going to call that out C. And over here we get, this is what was predicted. These two here, these are the actual placements. And so maybe we can compare the x1 with SNI, x2 with SCF. And we'll do that in a distance formula as well, like the Euclidean distance. We're going to say x1 is different from SNI. The bigger the difference, the worse that is, and we'll square that to see how far away it is from SNI, so on either side, positive or negative. And then same thing with cash flows. And then once we add those up and square them, we'll take the square root. So this is just another sort of distance function, similar to ones we have already encountered. And we're just going to save that and call it score unusual. So this is a score for what is unusual about that data or that observation based on these two-dimensional plots. So we'll do the other one that it's exactly the same. The only difference is we are going to use the standardized versions. So up here where I created the, up. Oh. Values. Okay, let me adjust this. I'm gonna have to adjust the one online too. I mean on the data frame. I mean on the script that I posted online. So now we want to do the sorry, I was confusing the homework with this. So I don't. So what we're going to do is just the affine version, which we talked about up here. So we're using this in the different calculation method, what I was thinking about is we could also use standardized versus unstandardized variables, but we didn't do that here. So, all right, we're taking the affine version. We're going to calculate we're going to predict based on that affine calculation, do the same thing. Everything else is going to stay the same. So we're going to calculate put the data back together and then calculate the unusual score for it. I'm calling it score unusual 2 so that we have two different versions of them. Then I'm going to combine these unusual scores back with the variables we need to merge it back into the original data, and then I'm going to left join the data. So we run this, you'll see that the out data frame has both unusual measures and the identifiers we can use. And then once we run this, we get this new training data. Not that one. That has now these two unusual 7, unusual 8, and we've collected these other ones as we've gone as well. Okay, the last one is called an isolation tree, and the isolation tree, like I mentioned, is trying to use a tree-based method to identify which observations are not close to other observations. So again, we're going to try the standardized version. And I'm just going to use all of these variables. We could use different variables, and maybe we don't want all of them, or maybe we don't want standardized, right? There are so many choices we can make here, but we're going to go ahead and create that model or the data. How we run this model is the function is isolation.forest. So that's just going to run through and come up with what is an isolated observation. That's what it calls it. So then we're going to predict with that ISO model and the data set we already created how unusual an observation is. Okay? So it takes a little bit. The ISO model, the isolation.forest is faster. The scoring each one takes a little bit longer. And then we can look at what those scores look like. And you'll see it's sort of similar to the scores we were seeing before, that more in the smaller range. There's not a huge range in these, but we get some that are closer to 1. So 0 is not unusual at all. 1 is really unusual. Okay, so we're going to save that last one as the unusual 9. Now we have 9 different versions of how unusual an observation is, and we're hoping that means those are anomalies that we can use to predict whether a company is going to manage their earnings or have managed their earnings. Let's go ahead and look at how correlated are these variables. So some of these were just versions of the same model. So 5 and 6 were just versions of the same. 7 and 8 were versions of the same. The rest are not exactly the same. So what I'm going to do is take the training data set, only select these columns that we're interested in, run the correlation function, and then round the correlations. And we look here and we see, notice the measure 5 is fairly correlated. It's highly correlated with number 6. Number 6 is fairly correlated with number 7, but not as much as 5 and 6 are. Sorry, no. So measure 5 and 6 are highly correlated. Then what we're interested in is number 7 and 8 those are highly correlated. So the ones where we made a change in either using a different method or standardizing the data didn't seem to change much. They're just highly correlated. The other ones, you see a few more that are correlated, but not near as much as those two. So then so we've got different measures is what I'm saying, but they're not all independent. Okay, so then the last thing that I want to do is then evaluate how well these worked. And the problem is that we have probabilities, and remember, we don't always get great numbers for probabilities because there's such a small probability to begin with in the data set that getting up to something that says this is a 70% probability is really hard. And then the other problem is that we're combining probabilities with scores about how unusual an observation is. So I created a different function. The reason I did this is so you don't have to go through and do all of this again, but what we're trying to do is create a confusion matrix. And if you remember, we did that when we tried to predict bankruptcy. And so we're going to do the same thing here. And so I created this new function. Let me just talk through what that function does. So we're going to have a column in our data set that is the outcome column. This is our earnings management, yes or no. It's 1 or 0. If there's earnings management, it's 1. And otherwise it's 0. Our anomaly variable column, so this is the one unusual 1, 2, 3, any of these, that's our anomaly variable column. And then I'm going to rank them by year, so we need a column that has the year information in that. So these are the things you need to put into the function to be able to make the function work. Then I'll just quickly go through how I created the function. So I'm separating those variables. I'm creating a data frame that I can use to calculate the confusion matrix like we did before. And how I'm going to do that is I'm going to call the thing that is predicted. If a company has a very high value, so notice this is if the anomaly variable is greater than, and quantile function, remember, tells you a percentile of the distribution. So we're going to look at the anomaly variable distribution, and if it's in the 90th percentile, that we're going to get the 90th percentile with this part of the function. So then it'll say if it's greater than the 90th percentile, we're going to call that 1. We're going to predict that that is an earnings management. Otherwise, we're going to call it a 0. Of course, 90% is arbitrary here. We could use something else as well. We don't really know what that cutoff should be. So we could mess around, change it maybe 95, or if it's, we see the distribution of earnings management, maybe it should be 99. We don't know. But what that will do is every variable, if it has a really high value, it's going to be 1 and 0 otherwise. And then just like we did before, if it's actually was an earnings management case and we predicted it was an earnings management case, then it's going to output, that's what we hope happens. And then also if it actually was not and we predicted it was not, that's also desirable. The other pieces are not desirable. Okay, so again, this is just to make it easier so you don't have to calculate this for every one of those yourself. Then let's just take a look. So I'm going to run this. So notice what I did is this first one is all earnings management, and it's all from this training data set. The training 2 is the one that has everything in it. Then we're taking all of these anomaly variables, unusual 1 through 9, and notice they all have the data frame, $ column, because you need to tell it an individual column for this function. And then the last one, the year, that's the same for all of them. So we run these, and it outputs confusion matrices for each of the variables that we use to identify anomalies. So let's just look through a couple of things. Let's focus on this yes and yes. That means you predicted, and I changed one thing in here, and that is, notice I'm dividing by the number of actual anomalies or earnings management that did happen, and I'm dividing here by the number of observations that don't have anomalies. That way we can look at these as percentiles instead of raw numbers like we had before. So here we have, and as you remember, and as you saw in here, the number of actual anomalies or the number of actual earnings management cases is really small. So when we're looking at 83% here, that's a small number compared to this 89% or even this 10% here. These are the actuals are really small numbers. So here we have, yes, we predicted it was going to be earnings management. So meaning it was in our highest level of our anomaly variable. And it actually was, ideally this would be 100%. So we got 16% of those right with the first one, 18% with the second one. So remember, this was just net income, this was just accruals. 2% of it right when we used the model of accruals. So failure here, that didn't work so good. I already noted some of this down for you. This one here, the net income one, again, worse. So these didn't help us at all. So number 5, is 10%. So we're better than these other models, but we're worse than the main thing, the first, just simplest versions up here. Then we adjust this, we do a different calculation for unusual, and it changed to nothing. So that didn't seem to matter. Then we got to the bivariate regressions or bidimensional regressions, and notice suddenly we're much higher. So 21%, that's the best of all of these that we've done so far. And we changed the calculation, didn't change anything either. So, that doesn't really matter. But the thing we did do is we got 21% of them right when we use the bidimensional regressions. Then finally, the last one, 18% of them right when we use the isolation trees. So, hey, we're doing, not as, it's better than these ones up here, but worse than the bidimensional ones. So the big question is, we don't know which of these is actually the most accurate or best one to use. And there are so many variables that we've included, that we've adjusted here. Some of the ones we've seen don't matter, but we could think about which variables should be in there. So for example, in the bidimensional regressions, where it did pretty well, then maybe different variables would have helped improve that more. Or here, same thing with the isolation trees. Maybe if we use different models or different variables or standardized, right? So all these pieces that we haven't really messed around with. On the other side, 20% that you get right is not terribly attractive, because if there's a substantial number of those that are going to commit earnings management that we haven't identified. So that's something that we might want to think harder about, right? Are there ways to, do we want to trade this off and say we'll get more of them, we'll call more of them ones that will likely have earnings management without, and we'll sacrifice that sometimes we're going to get it wrong. We're going to call them earnings management when they're not actually, right? This trade-off is something we have to think about. One of the ways we can do that trade-off is, remember in this testing part here, this function that I created for you, we're calling them, if it's 90% or more in that distribution, we're going to call them earnings management. Well, we could adjust this number, right? We could, if we changed it to, let's say, 75%, then maybe we would start getting numbers that are higher in terms of, yes, we got it right when it was right. Notice on the other side, this right-hand side, we didn't get much variation, right? Like normally, it was not an earnings management. We got some of them where we called it earnings management, and then others where it was not an earnings management, and we didn't call it earnings management. So in general, these don't affect any, like none of these seem to change much at all. So our model isn't affecting that. What would happen is if we change these numbers, we would start getting different proportions there. And that's something, we'd want to be careful with. All right, I know it's a lot, and we're throwing a lot of different methodologies and coding things to you. I tried to simplify it as much as possible. But as I think you'll see, and as you go through the homework, that it's not, when you don't have an observation where you're using a supervised model and you're just trying to identify anomalies without something else to determine whether it's an anomaly in the model itself, it creates some challenges and some interesting methods to be able to use. All right.